Welcome to qnawire.
Okay, so we have a solid uniform spherical boulder that starts from rest. Then, when it rolls down to the bottom, initially it crosses this rough surface and then it goes to the smooth surface. Now, the difference between these two is when the boulder crosses the rough surface, it has rolling without slipping, but in the smooth surface, it will slip while rolling. So, that means we need to break this problem into two parts. One is when the ball just goes to the end of the rough surface, we'll have to set the energy conservation at that point to the top. So let's actually mark three different points. One is this one, number one. We call this as number two, where that's the end of the rough surface, and then this is number three, which is the end of the smooth surface. Now let's do the energy conservation at the rough surface. So initially, let's first see what happens to the velocity. So since it's a rolling without slipping condition, so velocity v will be omega times r, where omega is the angular velocity and r is the radius of the boulder. And for the kinetic energy, since the ball has translational motion as well as rotational motion, so it will have rotational and translational part to the kinetic energy. So that's going to be half mv squared plus half of I omega squared. So that's the total kinetic energy that the ball will have while it's rolling through the smooth surface, the rough surface. Also, since it's a uniform solid spherical boulder, that means we can write I as 2 over 5 mr squared. Okay, now we're set to do the energy conservation. So here, at this point, let's call the height as h1. So we see that when the boulder is at the top, there's only potential energy. So we'll have mg h1, which is equal to, so when the boulder comes here, let's say the velocity is v, so the kinetic energy or the translational velocity is v, so the kinetic energy will be the translational part plus the rotational part, which is half of I omega squared. So we say that the rotational velocity or speed is omega. So that's our first equation. So we'll try to see what we can find out, or what we need to modify this equation so that we can use some information from this equation in the second part. So let's see what we can do here. So first of all, we can replace this I using this condition, and we can replace this omega using this condition. So that means we'll have the same parameters, or we'll have this equation or this part in terms of mv squared. So we can get rid of two parameters, I and omega, and write everything in terms of m and v. So let's see how we can do that. So we'll have mgh1 on the left, and on the right we have half of mv squared plus I is 2 over 5 mr squared, and omega is v over r. So we get this from this expression right here. So now we see that our equation only has v, m, and r. So, but then there's a square here, so we can get rid of this r as well. So this equation only has v and m components, which is easier to handle rather than having four different parameters. So if we calculate it, we see that first of all we can get rid of this m part, then this r part is gone as well. And then if we simplify this equation, we see that v squared is 10 by 7 G H1. So now this looks much better now. And so let me write down that equation one more time. We'll see in a second how we're going to use this information. So to use this information, we have to now deal with the smooth part. So in the smooth part, the ball is, or the boulder is, let's say around here. So we have to do the energy conservation at this point, and when the boulder reaches the foot of the hill, we'll have the energy conservation at that point as well. So at point number 2, we'll have mg2 or mgh2 plus, so that's the potential, and then we have the kinetic part, which is mv squared plus k rotational. We are not writing the expression here, and you'll see that in a second why we're not writing the expression. So in the right side, it's the bottom part where we have the translational kinetic energy, mv, let's call it bottom, plus the rotational part. And there's no potential energy because we're setting this as 0. So y equals 0 at this point. Y equals h2 at this point, and y equals h1 at this point. So there's no potential energy at the bottom. Now we can see that we didn't write the explicit expression for k rotation. And the reason for that is, since it's going through the smooth surface, then we'll have rotational energy on both sides, or rotation kinetic energy on both sides, so we can get rid of that. So we don't have to worry about that extra term. Now all we have is this, where we can also get rid of this m parts. And if we clean this a bit, we see we have gh2 plus half of v squared equal to half of v bottom squared. Now here we can use this piece of information where v squared is 10 over 7 gh1. And if we do so, we see that v bottom is equal to, there's a square root, then we have 10 by 7 gh1 plus 2 gh2, and then we put that under the square bracket, under the square root. And if we use the numbers here, we see that we have 10 over 7. Actually, let me write down the information over here. So h1 is 25 meters, and h2 is 25 meters as well, because as mentioned here, that the top half of the hill is rough, and the bottom half of the hill is smooth. So that means this right here is 25 meters. So this is 25 meters. And using that piece of information, we see that velocity at the bottom part is 29 meters per second. So as we can see, as we saw here, that we are treating um, two different parts. One is smooth and one is rough. And for the smooth part, we have k rotation on both sides, so we got rid of that. And then we use this piece of information from the rough part and replaced it over here to get the velocity at the bottom. Thank you.